Hi everyone. So in this project series, we'll understand how stochastic interest rate model works. So what you can expect from this whole project series is first understanding of what is stochastic interest rate model. So stochastic interest rate model is are used a lot in the world of quant finance, and specifically we'll be looking at the Vasicek stochastic interest rate model. So let me write Vasicek interest rate model, and then we'll see CIR interest rate model. We'll see the theoretical difference between the Vasicek and the CIR, and of course the Excel implementation. So in the Excel implementation, first we'll see how do we calibrate these stochastic models using a method called maximum likelihood estimator. And second thing that we'll see is how to implement. So after the models are calibrated, be it Vasicek or CIR, after the models are calibrated, we'll see the implementation piece of how these models can be implemented. So we'll see the implementation of Vasicek and CIR. Okay, so let me start with first what is a Vasicek interest rate model. So first I'll walk you through the theoretical understanding of Vasicek and CIR, or and then I'll show you the implementation piece. Okay, so starting from what is a Vasicek interest rate model? Okay, let me start with what is a Vasicek interest rate model. See, first of all, let's understand why do we need a stochastic, as I do, why do we need a stochastic interest rate model? Why do we need a stochastic interest rate model? Okay, let's understand first this, and then I'll tell you what is the Vasicek interest rate model. See, as the word stochastic. First of all, the word stochastic basically means random. Okay, the word stochastic means random. Okay. So what happens is if you look at interest rates, right? And when I'll show you the Excel implementation, you'll actually understand. Okay. So when you see the interest rates, let's say looking at the US 3-year treasury interest rates. Okay. So, if you see like stocks, like how we see stocks movement, right? Like how we see, let's say, how we see a stock movement of, let's say, Tesla or any company, let's say company XYZ. Okay. So we see that the stocks is moving something like this, right? So similar is the concept of interest rates. Interest rates also move like this, like this, like this, like this. Okay. So we always say that these movements, these if you see, let's say this movement, then this movement, it's coming down, then coming down, going up, coming down. We also get like daily data. We can also we get a daily data of interest rates. Okay, like how we get like the daily data of stocks, right? How we get the daily data of stocks. Similarly, we get a daily data of interest rate. And the pattern is always random in nature. We say that the pattern is random in nature. Okay, so when we say that this pattern, what you see of, so when we say that the pattern that we see of the stochastic of the interest rate is, so we say that the pattern of the interest rate is random in nature. Okay, basically the daily movement, how interest rate will move, it is completely random. So it can move up, down, down, up, down, up, down, up, down, up. This movements, these are completely random. So to model randomness, we need stochastic. Okay, And that's why we say these for modeling the randomness, for modeling the randomness of the interest rates, for modeling the randomness of the interest rates, we need what? We need a stochastic interest rate model. Okay, we need a stochastic interest rate model. So this is the theoretical piece, like why we are even going, why we are even understanding, or why we are even looking into stochastic models. So this is the reason, because see, uh, the interest rates are completely random in nature, and to model the randomness we need certain interest rate models, and that's why we are looking at stochastic interest rate models. So now coming back to what are different stochastic interest rate models in quant finance? The very first model that came into existence was the Vasicek interest rate model. Okay, this was the first stochastic interest rate model that came into existence in the world of quant finance. Okay, so this came in the year of 1977. Okay, this came in the year of 1977 and was introduced by Aldrich Vasicek. This model was introduced by Old Rich Vasicek in the year 1977. Okay, so what is this model? So basically, what we can say is the Vasicek model is a stochastic interest rate model which is used for modeling, the stochastic, which is used for modeling the interest rates. Okay, which is used for modeling the interest rates, or we can say that which is used to model, or which is used, let me write it again, which is used to model how interest rates how interest rates will move in the future. Okay, so this model basically tells how the interest rate will move into the future. Okay, so now let's see at the mathematical formulation of this model, right? Mathematical formula of Vasicek interest rate model. Okay, Vasicek. Okay, let me write it again. Vasicek. CEK. Okay, Vasicek interest rate model. So let's look at the mathematical formula of Vasicek interest rate model. So the mathematical formula of this of the Vasicek model is defined by dRt is equal to A times B minus RT dt plus sigma times dWt. Okay, so the equation is dRt is equal to A times B minus RT dt plus sigma dWt. So let's understand each and every component. Okay, first is RT, this component. So my bad. Sorry, I got a call in between. Okay, sorry. So let's see what is DRT. Okay, so DRT is A times B minus RT dt plus sigma dWt. So in this, let's understand each and every component. Okay, so let's understand what is RT. So RT is nothing but interest rate. RT is nothing but interest rate at time t. Okay, this is RT, interest rate at time t. Okay, So now what is A? A is nothing but the speed of reversion. Speed of speed of mean reversion. So what does it mean by speed? See, speed everyone knows, right? But what does it mean by speed of mean reversion? It basically means that it basically means that so this basically means that how fast the interest rate returns to the mean. Okay? So how fast does the interest rate returns to the mean? This is what it means by A. And don't worry, when I'll show you the Excel implementation, it will be very clear to all of you. B. What is B? B is nothing but the long-term average rate. Long-term average, long-term average rate. Okay. What is B? B is nothing but the long-term average rate to which the interest rate will revert. So you can always think a B as the equilibrium, or you can say let's say we have a data, right? We have certain interest. So let's say we have daily data of interest rates. Okay, let's say 3 year treasury data, treasury data we have. Okay, so we have 3 year treasury data. So when we take the average of this data, this is nothing but your B, which is your long term average rate. Okay. So we know what is A, what is B, what is RT. Now next comes is DT. What is DT? See, DT is nothing but small change in time. Small change in time. Okay. So because for us we are modeling the interest rate daily, so it will be 1 day, 1 by 252. Okay. Why 1 by 252? Because 252 is the number of trading days, okay, in a year. So you might be thinking there are 365 days, right? In a year, there are 365 days. But if you remove Saturdays, Sundays, and national holidays, there will be 252 days. Okay. So basically, we are modeling our interest rate for 1 day. So 1 by 252 will be a small change in time. Okay. So dt is nothing but 1 by 252, which is small change in time. So now we have covered dt, a, b minus rt. Now what is left? Sigma. Sigma is nothing but your standard deviation. Sigma is nothing but Sigma is nothing but your standard deviation, or you can say the volatility. You can say volatility. Okay. The volatility of the interest rates. Volatility of the interest rate. Okay. Now the next component is what? DWT, right? Next component is what? DWT. So what is DWT? So DWT is nothing but it is the Wiener process, right? It is the Wiener process, or you can also say as Brownian motion. So this is used by, so DWT is represents what? The randomness. So this term represents what? It represents It represents the random or the unpredictable fluctuation that you see in the interest rates. Okay, it represents the random or the unpredictable fluctuation that you see in the interest rate over time. Okay. So, I was telling that, like you will see interest rate going up, then coming down, right? This is actually it goes in a very random fashion. This process goes in a very random fashion, and this is actually been modeled by what? This has been modeled by Brownian motion. you know this is being taken care by the Brownian motion. Like will it move up, down? This randomness will be modeled by the Brownian motion. Okay. So now you might be thinking, Okay, yeah. So what is the DWT? Here, formula of DWT is nothing but ZT times square root of delta T, where ZT is what? It is a random number generated from a standard normal distribution. So I'll also showcase this, how this works. But as of now, I just want you to understand that DWT is nothing but it represents the randomness or the unpredictable fluctuation that you see in the interest rates. And why do you see? The question is, why do you see the fluctuation in interest rate? So the question is, why do you see, or why do you see fluctuation in the interest rate? See, there can be multiple reason, right? There can be multiple reason for when you see fluctuation. It can be because of certain economic news, right? Or some policy changes or some market sentiments, right? It can be anything. And that's why, to model this randomness, to model this all this behavior, we use what? Brownian motion. So DWT is nothing but your Brownian motion, okay? This is nothing but your Brownian motion. Okay. So we saw what is sigma and what is DWT. Now what is DRT? So DRT is nothing but the change in interest rate, okay? See, DT is nothing but change. See, DT is nothing but change in time, right? Similarly, DRT is nothing but change in interest rate, okay? So here DRT is what? DRT is what? DRT is nothing but change in interest rate. Okay. So let me write this equation again and let me summarize the whole formula. So the equation, so Vasicek interest rate model equation is what? So the equation is nothing but DRT is equal to A times B minus RT dt plus sigma DWT, right? Now again, A is what? Speed of mean reversion, right? So this speed can be high or low, okay? B is nothing but the long-term average mean or long-term average. So long-term mean, or you can say the long-term average of interest rates. Mean or average is just the same thing, okay? So we covered A, B. What is R rate? RT. RT is nothing but interest rate at time T, okay? Interest rate at time T. DT is nothing but small change in time, which is nothing but 1 by 252. Then we have sigma, which is nothing but volatility of interest rates. Okay. And the last component, DWT, is what? Brownian motion or Wiener process. You can say Brownian motion, or you can also say as Wiener process. It's just the same. These are synonyms which can be used, either you say Brownian motion or either you say Wiener process. It is just the same. Why we use DWT? So that it can be used to model the randomness that we see in the interest rate. Why do we see the random fluctuation of the interest rate? Because there can be multiple reasons. There can be economic changes or economic changes or policy changes or any unexpected behavior that you see in the market. There are a lot of reasons. Now the question is how A and B, okay, and DT, last component is DRT, which is left. DRT is nothing but it is nothing but change in interest rate, right? DRT is nothing but change in interest rate. Okay. Now the question is, what is the use of the speed? What is the use of the long-term mean? Okay. This is a question, or let's say, what is the use of this? What is the use of A, which is the speed? What is the use of B, which is the long-term mean, right? So let's understand where this, or RT, which is the interest rate at time T. Let's understand how are we using it. Okay. Let's see how we are using it, or why is it important to you, where how are we using it? Let's understand. So let's understand the interpretation of A, B, R, T. Okay. Also, one more thing which I wanted to make you understand is if you see this part, which is A times B minus RT dt, this is called the deterministic part, and this part is called the stochastic part. Okay. So just to make you all understand, the first part, which is A times B minus RT dt, is called the deterministic part, and the second part is sigma times dwt is what we call as stochastic part. Okay. So just for the all of you to make you understand, A times B minus RT dt, this is the deterministic part of the deterministic part of the Vasicek interest rate model. Deterministic part. And this component, which is sigma dwt, is the stochastic part. Okay. So now a quick question is, what is deterministic and what is stochastic? See, if you see why we say this as deterministic, because we have value of A, B, RT and DT. Okay. We have values of this. So it is, it can be determined. Okay. So let me give you a better example. Okay. Just give me 1 second. Okay. So if you see, sigma dwt is called the stochastic part, right? So why is it called the deterministic part? See, the deterministic component drives the interest rate towards the long-term mean. Okay. So this component is called the mean reversion component. Mean reversion component or deterministic component. Why do we say that? Because it drives the interest rates towards. So why do we say this as mean reversion component or a deterministic component? Is because this component, this A times B minus RT dt, it drives the interest rates towards the long term mean. Okay. And why do we say as this is stochastic? Because it captures the random and unpredictable behavior of the interest rate. Or you can say it captures the random and unpredictable deviations from the deterministic trajectory. Okay. Basically, basically what I'm trying to say is this component, which is A times B minus RT dt, this is the deterministic component. What's the aim, or what's the goal of this deterministic component? Is it drives the interest rates towards the long term mean, which is B. Okay. And what is the essence of the stochastic component? Basically, it captures the random or unpredictable deviation, or you can say it captures the random or the unpredictable behavior that you see in your interest rates. And let me show you with the help of a quick, I would say, example of how this deterministic component drives the interest rates. Okay. So see, what is the component? The component is this. Okay. So the mean reverting component is what? A times B minus RT dt. A times B minus RT dt. Okay. So tell me one thing. When when RT when RT is greater than when RT is greater than B, when RT is greater than B, what will happen? So let's assume that dRT is equal to A times B minus RT dt. Okay. Let's just take the deterministic part as of now. Okay. Let's just consider the deterministic part and the sigma dWt. Let's leave it aside for a moment. Let's leave it aside for a moment. Okay. So let's say our dRT is equal to the mean reverting component. Okay. Or deterministic component. Okay. So let's tell me one thing. Case one is when RT is greater than B. So when RT is greater than B, what will be this? Positive or negative? Can you all tell me? So when RT is greater than B, so B minus RT will be positive or negative? Correct. This will be negative, right? So if you see, so basically what will happen is because this component DRT, so so if this is negative, this whole component will be negative, right? This everything will be negative because what we are doing, we are see some just imagine something like this. If we are multiplying -1 with positive numbers, it will still give us negative number, right? Similarly, if we are multiplying this negative with these two positive numbers, it will still give us a negative number. So dRT will be less than 0. So dRT will be less than 0. So what will happen if the interest rates, if the change in interest rate is negative? So what will happen is, see, if let's say the interest rate is like this, it will move downwards. At this point, if DRT is, if change in interest rate is negative, it will move downward. Okay, so what will happen? It will adjust the short rate process. Short rate is nothing but DRT, okay? This is the short rate. Adjust the short rate downwards. Okay? Did you all understand what happened? Did you all understand what happened? So basically what I'm saying is, if RT is greater than B, DRT will be negative. What is DRT? DRT is nothing but change in interest rates, right? So let's say right now, let's say something like this happened. Okay, this was like last 1 week data, and right now at t equal to 0, we are here. Now it's saying that this change in interest rate is negative. So when will it be negative? So if it's negative, it will pull it downward. Okay, it will pull it downward. And if DRT is positive, what will happen? It will pull it upwards, right? So something like this. If DRT is positive, it will go up. Okay, it will go up. So let's say so this was case one. This was case one when RT was greater than B. Let's see case two. What is case two? When RT is less than B. This is case 2 when RT is less than B. Now let's look at the equation of mean reversion. dRT is equal to what? A times B minus RT dt. This is a mean reverting component. So what I'm saying here is B, this component B is greater than RT. So this will be what? Positive. B minus RT is what? Positive. So when I multiply positive with dt and A, dRT will be what? This whole component. So when I multiply this positive with these two numbers, DRT will be positive. Okay. So what will happen? So when DRT is positive, it will adjust the short rate process upwards. Okay. It will adjust the short rate process upwards. Okay. So now you might be thinking that Mehul, you have said this A and DT is positive. Why I'm saying this is, see, dt is anyway time, right? It is 1 day, so it is 1 by 252. So this is a positive number. And A is what? Speed of reversion, speed of mean reversion. See, if you see, speed is always positive, right? Have you ever heard that, oh, speed is okay? So take an example. I was, riding my motorbike at 10, let's say, 10 miles per hour or 10 kilometer per hour. So it is speed is always positive, right? It cannot be negative, and that's why I say, this a and dt term is always positive. Okay, a and dt term is always positive. So this the direction of the short rate. Okay, so therefore the direction of the short rate depends on what? The direction of the short rates depends on the value of b and rt, right? So what we saw? So we saw that b if rt is greater than b, drt will be negative, will be less than 0. Therefore, it will adjust the short rate downwards. Similarly, this was case 1. And if rt is less than b, so what was the equation? If you all remember, a times b minus rt dt, right? So if b is greater, if this is greater, drt is greater than 0, or you can say drt is positive, and it will adjust the process upwards. Okay? Is this clear to everyone? So this is how we use the concept of A and B. This is how we use the concept of A, B, RT, which is like which is our the mean reverting component. Okay. So always remember the first part. This first part is the mean reverting component or the mean reversion, or you can say deterministic component. And the second part, sigma DWT, it is called the stochastic part or the stochastic component. Is this clear to everyone? Okay, perfect. So this was the Vasicek equation. And when I show you the Excel implementation, you would just love the concept. But let me, first make you understand the theoretical piece because theory is very important. So now the question is, see, every model that you see in quant finance, be it a pricing model, derivative pricing model, be it a stochastic interest rate model, or be it a stochastic volatility model. So let's say because we are focusing on stochastic interest rate, so let's keep it up till there. So every model has certain strengths and limitations. Okay, so every model has some strengths and limitation. So let's look at the strength and limitation of Vasicek interest rate model. Okay, let's look at the strength and limitation of the Vasicek interest rate model. See, first strength is it is okay. Let's first see the strength. Strength is it is very intuitive. Okay, first strength is it is intuitive. Intuitive. What does this basically means? This basically means that, see, the concept of mean reversion actually aligns with how people might think about the interest rates. Okay, see, if you see the formula, which is drt is equal to a times b minus rt dt plus sigma dwt. If you just see, it is a very simple equation, right? If you just see, there's nothing complex involved in it, so it is very intuitive to understand. Okay, and even if you see conceptual wise also, it makes this the concept of, if you see conceptual wise also, the concept of mean reversion aligns with how people aligns with how people or aligns with how many people think about interest rate returning to the normal level after periods of highs and lows. Okay, see, you will always see, this all these models, these were like geniuses, people like great researchers. They, if you they worked so hard to build these models. And these models make sense also. If you see like interest rates, just see at any interest rate. Have you ever seen interest rate going up, 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 up? Or have you ever seen interest rate going down, down, down? It will never happen. What you will basically see is interest rate will go up, then the government of the country will come and it will pull down the interest rate. Similarly, rate will go down, and the government will interfere and say, now the interest rate should be up, right? And sometimes, and sometimes, yeah, correctly mentioned, sometimes it can be stable also, and something like this you can always observe. So what is this part? So if you see this part, which is increasing trend, so this is nothing but DRT, right? The DRT is positive. Here what DRT is negative, right? And one more thing which I wanted to make you understand, these are, see, if you remember this B component, what was it? Long-term mean. Long-term mean. So what this basically says? So what this basically says, if it goes up, you know, A B minus RT dt. This B component is what? Long-term mean, right? Long-term mean. So what it says, see the Vasicek, what Vasicek was trying to say was there will be a level, this long-term level, okay? There will be this, okay, sorry, there will be this long-term level, long-term mean of interest rate, okay? Let's say this is 5%. Okay, let's say this long-term mean is 5%. So what Vasicek was trying to say was, let's say we saw a period of high, then it will come down, and again it will go up. So it will always oscillate at a long it will always oscillate at certain mean of the interest rate. Okay, it will always oscillate between certain mean of the interest rate. And that is what we also see in the economy also, right? I mean, sometimes interest rates are up, sometimes interest rates are down. It will never happen that interest rates are just going up or interest rates are just going down. It will never happen. You'll always see interest rate going up and down. Okay. So now, so this was the first strength, which is, it is intuitive. So a quick question is, okay, so a quick question is, long-term mean is considered for how much periods? Okay, that's a very good question. That depends on what kind of period are you taking? Because if you remember during the COVID period, right, interest rates were very low. I remember back in India during the COVID period, interest rates were really low, and now if you see interest rates have become high. So it actually depends on, so the number, so this level of interest rate, which is the long term level, actually depends on how many years of data are you considering. Okay, how many years of data are you considering? So sometimes you will just consider 1 year of data, sometimes you can also consider 10 years of data. It totally depends on you, how many years of data you are considering and what's the use case. That is also very important. So also, okay, so this was first thing, that it is intuitive. It is, this the whole model makes sense because in real life we see interest rates going up and down, and that's what we also see from the model. Now the second thing is, and it is second strength that the model that this Vasicek has is analytical. It has an analytical solution. It has a analytical solution. So what does it mean by analytical solution? If you all remember, you saw something like this: a square minus. You might have seen some equation, a quadratic equation, right? Let me. So, what does it mean by analytical solution? Analytical solution basically means that it is possible. So, analytical solution basically means that it is possible to derive a closed form solution. Okay, it is possible to derive a closed form solution for certain problems, or you can say for certain use cases such as bond pricing, or it can be also used for risk management purposes. So, basically what I'm trying to say is it has a closed form solution. So this was the second strength. Okay. Now Now let's look at certain limitation. Okay, let's look at certain limitation. Okay, so a quick question is, what is a closed form solution? See, the thing is, if you see, let's say if I give you x plus 2 is equal to 5, right? So what will be the closed form solution? So we can basically solve this equation, right? Similarly, similarly for Vasicek also, you can actually solve this equation to get a closed form solution. Okay, you can solve the whole this whole equation of, okay, let me write it again. So you can again solve this equation to get a complete closed form solution. You can solve this equation to get a complete closed form solution, and this closed form solution can be used, and or you can say it is used most of the time for bond pricing. But let's not go there, because let's just understand that this the interest stochastic interest rate model like Vasicek has a lot of use case, and one of the use cases bond pricing, and the other use cases it is used a lot for risk management purposes. Okay, so these were the strengths. Now let's look at the limitations. Let's look at the limitation of this model. See, the limitation is, first of all, the first limitation of this model is, this model actually generates negative interest rates. This model generates negative interest rates. Okay. See, certain like models like Vasicek can be very useful where the interest rates are very low. I remember Germany has a very low interest rate, very close to zero. So it can it I have also seen, in Germany the interest rate going negative. Okay. So in such cases, Vasicek model actually works, pretty good because it generates negative interest rate. But let's say USA, right? The economy, if you see the economy, it has a higher or positive interest rate. Same goes for India, right? It has a positive interest rate. So sometimes using such model actually, it gives you negative interest rate, which which does not align with the real world, because in real world that the interest rates are positive, but this model can actually generate a negative interest rate. So so the first limitation that this model has is, it can produce a negative interest rate. It can produce a negative interest rate, which can be unrealistic if in case the interest rates are high. Okay, are high. So this is the first limitation. Okay, that it generates a negative interest rate. It can produce a negative interest rate. Okay. So what are so if you see, let's say USA, India, Pakistan, Sri Lanka, right? China. If you see all these countries, they have like a much higher positive interest rates. So models like this will be, not good for certain economies like this. But if you see Germany, Japan, where they have negative interest rate, models like this will work great. So you might be thinking, oh, I'm based out of India or I'm based out of USA. Why should I learn these models? But you can also, it can be the case that you can also interact, or you can also, work in certain financial instruments which are based out of different economies. So you can actually trade different financial instrument which is based out of Germany. So that's why you should understand these models, because it is not that you will have exposure in only one market. It can happen that you can have exposure to multiple markets altogether. So that's why understanding certain models like this is important. So moving on, this was the first limitation, that the interest rate can go negative. Second limitation. See, second limitation is, it is a single factor model. It is a single factor model. So what it means is, the if you see the volatility, or you can say, okay, just give me 1 second. My pen is not working. Just give me 1 second. Okay, yeah, I guess now it's working. Okay. So it is called a single factor model. So what happens is, the model is driven by market risk. The model is driven by market risk, which is the only factor affecting the changes in interest rate. Okay. See, if you see this equation, plus sigma dwt. See what is changing. See, A is constant, B is constant, dt is constant, sigma is constant. dwt is only changing, right? And this accounts for your market risk or the randomness, right? So that's why it is called, or you can say that's why we always say that um, these models are a single factor model. Okay. We always want certain models which have like multiple factors. Okay, we always want models which have like multiple factors, so that multiple factors can affect our interest rate. In this case, only a single factor is affecting our interest rate. So a question you might be asking is, which factor is actually causing interest rates to be negative, right? Which factor is causing interest rates to be negative? So if you see the stochastic part of it, if you see the stochastic part of it, the stochastic part of it is responsible for negative interest rates. Okay, okay, stochastic, because we are, if you remember what was dwt term. Dwt was, we were generating random numbers, right? We were generating random numbers from a standard normal distribution, right? We were generating random numbers from a standard normal distribution. That's why it is responsible for generating negative interest rates. So now, so now let's see how can we calibrate. So see, guys, this was all about the Vasicek model. Okay, this was all about the Vasicek model, which is dRt is equal to A times B minus RT dt plus sigma dwt, right? This was our Vasicek model. DRT is nothing but small change in interest rate. Okay, this is nothing, small change in interest rate. A is nothing but the speed. B is the long term mean. RT is the interest rate at time t. DT is small change in time. Sigma is volatility of interest rate, and DWT is the Wiener process, which actually accounts for the randomness, or which captures the randomness in the interest rates. Now let's look at the calibration of this model using the market data. So what happens is, every time you need to calibrate these models through the market data. So the calibration technique that we'll look into is maximum likelihood estimator. And guys, after this we'll see the practical implementation of this in the next video. So this is MLE, which is maximum likelihood estimator. So now let's see what is MLE, or what is maximum likelihood estimator. Mostly you might have studied the concept of MLE in your statistics class. Okay, and it is mostly used for parametric estimation. Okay, so if you see, MLE is a method. The MLE is a method which is used to find the best fitting parameter of a or best fitting parameter for a mathematical model. Okay, for a mathematical model based on the observed data. So you might be thinking how, or you might be thinking why is it used for finding the best fitting parameters of the model, right? Vasicek is a mathematical model, right? So if you remember this equation, which is what dRT is equal to A times B minus RT dt plus sigma dWt. So what we are doing is we are trying to find these A, B, and sigma. So we are trying to find A, B, and sigma using MLE. Okay, so will be basically how will we? So if you see dt is what 1 by 252, right? And dWt is what? It is nothing but Brownian motion, or it is, you can also say it is a random number generated using standard normal distribution, right? So these two is already given, or these two will already calculate, but this component A, B, and sigma, this is being calculated using MLE. Okay, this is what. Okay, so I guess okay, there's a also. So if you, so I guess on the there's a question that I see. What is responsible for the negative interest rate? Yeah, I agree that someone basically wrote that if RT is greater than B, then we see negative interest rate. I agree. This part is also, see, when you see both the components, both the components actually account for negative interest rate. I'm not denying that. So because if RT is greater than B, we'll see this component as negative and this component as negative. But when we'll see a CIR model, which is the extension, or you can say which is the improvement of the Vasicek model. So I'll tell you, so basically this what CIR did was they made adjustment into the stochastic part of the Vasicek model. And as soon as they made the adjustment in the stochastic part, then the model was generating positive value. Okay, then the model was generating positive value. So we'll come to CIR. I know you might be thinking we should have a model which generate positive interest rates. I know that, and that is actually covered in the CIR part. So just wait for few minutes and few sessions, and actually I'll show you how CIR generates positive interest rates. But let's look at the calibration piece first, of Vasicek interest rate model. Okay, just give me 1 second. Let me drink some water. Okay, so basically, you might be thinking how this concept of MLE works. See, what MLE does is it will adjust your model. It will adjust the model, and it will make sure that whatever your data is available in the market, or whatever you see interest rates in the market, the model actually predict those. Okay, so what MLE does is okay, you'll have some actual data of interest rates, right? You'll have this actual data of interest rate, and then you will generate interest rates using the Vasicek model. Yeah, right. You'll have some actual data of the interest rate, and you'll generate interest rate using the Vasicek model. So now what MLE does is it will make sure that it will adjust the parameter. It will adjust the parameter in such a way. It will adjust the parameter in such a way that the values generated from the Vasicek model closely aligns with the actual data. Closely aligns with the actual data. Okay, and that's how, that's why we calibrate these interest rate model. Otherwise there would be no sense, right? If let's say actual interest rate is 5%, and my check model is generating 8% or 7%, This model will not make sense, right? Because it is very far away, 2% or 3% far away. So that's why there is a need of calibration. So this MLE method will adjust the parameters in such a way, which all parameters A, B, and sigma. Okay, it will adjust the parameter in such a way that the interest rate which will be generated through this Vasicek model, that will actually align very closely with the actual data. Okay, so now let's understand how Emily does it. Okay, let's see how Emily does it. So the very first step is, so let's see how Emily does it. How Emily does it, or how the concept, how maximum likelihood estimator works. Okay, let's see how maximum likelihood estimator works. See, first of all, what we'll do is will have will okay, so the very first step is we'll have the actual data. Okay, we'll have the actual interest rates from the market. Okay, we'll basically download the actual interest rate from the market. Okay, so let's say we have certain, let's say 5%. Okay, let me give you certain example. We have like 5%, 5.1%, 5.05%, 5.15%, and so on. So this is our actual interest rates. Then we'll have our Vasicek interest rate model. Okay. Okay. So which is, let's say, let's say this generates something as 4.5%, 4.75%, 4.6%, something like this, and so on. So now what is the sorry, excuse me. So what is the first step? If you all remember the equation of Vasicek, A times B minus RT dt plus sigma dWt. Tell me one thing, are we modeling the interest rate, or are we modeling the change in interest rate? Can you tell me? Are we modeling the interest rate, or are we modeling the change in interest rate? That's correct. We are modeling the change. So the first step is calculate the change in interest rate, right? This is change in interest rate actual. So what you'll do is you'll basically, so let's say this is today, t minus 1, t minus 2, t minus 3, and so on. This is the value today, and this was the value yesterday, day before yesterday, and so on. So how will you calculate the change? 5% minus 5.1%, 5.1% minus 5.05%, and so on, right? This is your modeled, this is your actual change in interest rate. And similarly, you'll do what? You'll actually use the Vasicek model, right? You'll actually calculate what is the change in your interest rate through the Vasicek model. So similarly, you'll do 4.5% minus 4.75%, 4.75% minus 4.6%. So you'll subtract these two, then these two, right? So on, you'll calculate the change in interest rate. This is the very first step. This is the very first step. So you have the actual interest rate, you have the Vasicek interest rate model. So the first step is to calculate the change in actual interest rate and change in interest rate through the Vasicek model. Now, now, so let's say this is step one. This is step one. So this was step one. Step two is what? So now we have gotten change in interest rate actual, change in interest rate using the Vasicek model, right? Let's say 0.005%. I'm just giving some random examples: 0.0025%, 0.004%, and let's say this is 0.01%, 0.002%, 0.005%. Let's say this is, when you subtracted these two values, these two values, and you got this number, right? Actual number. And when you subtracted these two values, sorry, my bad. So when you subtracted the actual values, which is these two, you got this number. Okay, I know the numbers are not matching, but I'm just giving an example. Okay, and when you are subtracting these two numbers, which is these two values, you are getting this number. So you'll get this whole series. Okay, You'll get this whole series. This is the first step. Second step is calculate the residual. Calculate residual. Okay, first step was calculate DRT. Okay, step 1 was calculate DRT, which is nothing but change in interest rate. Okay, this was first step. Second step is calculate the residual. How will you calculate the residual? Residual is simple. So residual is equal to change actual, whatever actual change in interest rate versus the versus the Vasicek model. Okay, so you'll use this formula. Residual is what? Actual minus the modeled value. Modeled value is what? Using the Vasicek model. So you're just subtracting these two values. Just subtracting these two values. So just subtracting these two values. This is step 2. Okay. So on you'll get these values. Step 3 is, what is step 3? Take normal distribution. Take a normal distribution of the residuals. Take a normal distribution of the residuals with mean of 0, and variance or and standard deviation of sigma. Standard deviation of sigma. What does that mean? So if you all remember, what we are doing is we are saying that this residual is normally distributed. This residual that we have calculated is normally distributed around the mean 0, is normally distributed around the mean of 0. Okay, tell me one thing. Okay, tell me one thing. This residual is what? This is nothing but your error term, right? This residual is what? It is nothing but your error term, right? What is the error, or what is the difference between your actual value and your Vasicek value, right? That is nothing but your residual, or you can also say as error. So when we say that this error is normally distributed around the mean of 0, what we are trying to say is, residual is actually the error term. See, error term is basically what I mean to say is, see, what is an error? See, let's say you observe some actual data, and you are using a model to generate interest rates. So what will be the error? This minus this minus this, right? This is nothing but your error term, right? This minus this is your error term, right? So tell me one thing. Do you want to minimize the error or maximize the error? Tell me one thing. Would you want to minimize the error or maximize the error? You always want to minimize the error, right? You always would love to minimize the error. And if I say that error has become 0, that is the best thing, right? That would be the best thing, right? So what I'm saying is, my my residual or my error term is normally distributed with a mean of 0. Basically, I'm saying that let's make this all 0. Let's try to make this residuals let's try to make this residual all 0. Okay, whatever difference you see between the actual and the modeled value of interest rate, let's try to make it all 0. Okay, so this is step 3. Okay, this is step 3, and the last step is what? Take take last step is what? Take log. So this is basically step 3 is called the likelihood function. Okay, step 3 is called the likelihood function. Okay, step 3 is called the likelihood function, in which we are saying that the residual or the error term is normally distributed around the mean of 0. And the next step is step 4 is take log likelihood. Okay, take log likelihood. What do I mean by log likelihood? Basically, okay, your this is your actual, this is your using your Vasicek model, then you calculate your residual or your error term, right, which is this minus this. Okay, then you have calculated certain residuals, right? Now you take a normal distribution of this residual. Okay, so you'll get certain values. Now what I'm saying is just take log of these values, whatever value you see, just take log of, let's say, x1. Okay, let's say this is x2. Similarly, this is x4, x3, x4, x5. Just take log of these value. Okay, after taking log, what you do is just sum up, just sum this value, just sum all of these values. Okay, and this then try to maximize it. Try to do what? Try to maximize this value. Okay, try to do what? Try to maximize this value. And how will you maximize this value? By changing the parameters like a, b, and sigma. Okay, and that's how, and this is what we say as the concept of maximum likelihood function. Maximum likelihood function. We are trying to maximize the likelihood of the function. What does this say? We are trying to maximize. We are trying to maximize the likelihood of this function. Okay, we are trying to maximize the likelihood of the function. How are we trying to maximize? By changing the parameters such as a, b, and sigma. So we are changing these parameters to maximize our likelihood function. So guys, let me recap this for all of you. So how do we calibrate the Vasicek interest rate model using the MLE method? And see, these all are statistical method which you will be using in some or the another way. Okay. First step is calculate change in RT, because see, what are we trying to model using the Vasicek equation? Vasicek interest rate equation. We are trying to model the change in interest rate. So this is very easy. First calculate whatever interest rate values you have. First calculate the change in interest rate. So calculate the change in actual interest rate and change in the interest rate through the Vasicek model. This is the first step. Okay. This is the first step. Second step is, since you have already calculated the change in interest rate, calculate the error term, which is the error term through the actual data and through the Vasicek model data. So then we get this error term. This was step 2. Step 3 was take the normal distribution of this error. See, what we are trying to say is we want to minimize this error. What is the minimum value that the error should take? It should be 0. We are saying that there should be no difference between the actual data and the model Vasicek data. Okay, between the actual interest rates and the interest rates coming through the Vasicek model. So that's why we are saying that let's make this error normally distributed with a mean of 0. Okay, and a standard deviation of sigma. Okay, so this is what we are doing by saying that we are just normalizing the error around the mean of 0. Okay, normalizing the error around the mean of 0. This was step 3. Step 4 was take likelihood. So what happened was, this was the change in interest rate, actual interest rate, change in the Vasicek interest rates. We calculate the error term, then we are saying it's normally distributed. And then the last piece is take the log of this function, and then after taking log of this, just add all of these, and we need to maximize this sum. Okay, we are trying to maximize this sum. How will we maximize? By changing the parameters of a, b, and sigma. So so since we are doing in Excel will change the values of a, b, and sigma, and wherever we get the maximum value of this, it will say that yes, these are the right values of a, b, and sigma. Okay, that's why the name is given maximum likelihood function, that we are trying to maximize the likelihood of a function by changing the parameters such as a, b, and sigma. Okay. 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 So a quick question asked is why we are taking the log. Okay. That's a very good question. Why are we taking log? Why are we taking log? And that's a very good question. Okay, so since we are working with multiple time steps, okay, since we are working with multiple time steps, okay, see, if you remember, it is not just 1 day data. We are dealing with almost a 1 year data, or 5 year data, 10 year data, right? So, if you see, since we are working with multiple time steps, since we are working with multiple time steps, the total likelihood of the entire data set, the total likelihood of the entire data set is nothing but the product of likelihood of each individual time steps. Let me explain you. So basically, if I want to calculate, see, this is maximum likelihood function, right? So if I want to calculate likelihood, how will I calculate likelihood? So we basically multiply, x1 times x2 times x3 times x4 times x5 times. Now just imagine, if let's say x1 let's say x1 is 10, x2 is 10, x3 is 10, x4 is 10, and we have, let's say, 5 years of data, and everything is 10, 10, 10. Just imagine how computationally expensive it will be, right? When I say computationally expensive, I'm not saying in terms of money, I'm saying in terms of time. It will be very time consuming to run this process. And we know that mathematics is so beautiful that we got introduced with log, right? So we know that if, let's say, we have a times b times c times so on, if we take log of this, log of a times log of b times c times, so what is this? Log of A plus log of B plus log of C and so on, right? So what we did was, we are taking log of this and adding up. This thing is same as saying, this thing is same as saying A times B times C times log. So the reason why we are taking log is to make this whole process easy and to make it less computationally expensive. Okay, and that's why we use log, and that's why how this whole process becomes easy, very easy. Okay, so in the end, we are taking log of each component. We are taking log of each component and then adding it up to get. And after adding it up, we are trying to maximize the sum by changing the parameters of a, b, and sigma. So is this concept clear to everyone? Is this concept clear to everyone? Any doubts you guys have? So just to make you just to summarize it last time, oops, okay, my bad. Just to summarize it last time, summarize the calibration process last time using the Emily method, and after this we'll see the Excel implementation. First, you calculate DRT using both your actual data, actual interest rate data, and using the Vasicek model. This is the first step. Second step is calculate the error term. You can say calculate residual, okay, or you can say error between the actual and the Vasicek model. Third step is take normal distribution of this error, or let's say take the normal distribution of the residual with a mean of 0 and a standard deviation of sigma. Why mean of 0? Because we want that these residual should be 0, right? And when this residual is 0, what does this means? That the actual data is same as the Vasicek data. Okay, and the last step is take log of whatever value you have got using the normal distribution, and sum all the logs, right? And try to maximize this sum by changing the parameters of a, b, and sigma. And that's how you perform a calibration of the Vasicek interest rate model using MLE. So guys, that was all. If in case there is no further question, I would like to walk you all through the Excel implementation. But just last minute, if in case you have any doubts, please feel free to ask. I'll wait for just 1 minute. If in case any doubt, please feel free to ask in the chat. Okay, so a quick question is how to calculate. Okay, so there's a question how to calculate volatility of the interest rate. So that we'll see how do we calculate in the Excel implementation. We'll see how we calculate the volatility piece, okay, of the interest rates. So we'll see in the Excel implementation of how to calibrate each and every parameter, okay. We know the Vasicek interest rate model. We'll see each and every parameter, and let me, quickly walk you through the Excel implementation. So let me stop recording, and in the next session, I'll show you how to I'll show you the Excel implementation of the Vasicek.